Alright, so let's talk about chips, not the kind you eat, but the silicon brains that power pretty much everything we love about modern tech. For years, the conversation has been dominated by CPUs and GPUs. The CPU is your device's general manager, handling all sorts of tasks. The GPU is the graphics specialist, amazing at rendering everything from your phone's user interface to the latest video games. But as artificial intelligence, or AI, has become more a part of our daily lives, a new class of specialized processors has stepped into the spotlight. These are the unsung heroes working behind the scenes to make our devices smarter, faster, and more efficient at AI tasks. Enter the NPU and the TPU. These acronyms might sound like alphabet soup, but they represent a huge leap forward in computing. NPU stands for Neural Processing Unit and TPU stands for Tensor Processing Unit. Both are a type of AI accelerator, which is a fancy way of saying they are custom-built to handle the specific kinds of math that AI and machine learning models run on. Instead of making the general-purpose CPU sweat over these complex calculations, devices can offload the work to these specialists. This means faster performance, better battery life, and capabilities that just weren't possible a few years ago. So, what's the fundamental difference? Think of it like this: an NPU is like having a personal AI assistant built right into your smartphone or laptop. It's designed to run AI tasks efficiently, right on your device, without needing to constantly talk to the internet. On the other hand, a TPU is like a massive, supercomputer-level brain living in the cloud. It's built by Google to handle the heaviest, most demanding AI training and processing jobs imaginable. Both are driving the AI revolution, but they operate in very different arenas and are designed for completely different scales of work. Understanding the distinction between these two is becoming more important every day. It's not just for tech nerds anymore. The type of processor in your next phone, car, or even smart home device will directly impact what it can do and how well it does it. This isn't just about raw speed, it's about enabling new features, protecting your privacy by keeping data on your device, and shaping the future of how we interact with technology. So, let's dive in and break down what makes each of these chips tick, where you'll find them, and why this tech showdown matters to you. So let's start with the NPU, the Neural Processing Unit. You've probably heard this term thrown around during the launch of a new smartphone. Companies like Apple, Samsung, and Qualcomm love to talk about their latest NPU. At its core, an NPU is a microprocessor designed specifically to accelerate machine learning algorithms. It's all about doing one thing really well: neural network computations. These are the mathematical models inspired by the human brain that power most of the AI features you use every day. Think of it as a dedicated specialist on your device's team. The magic of the NPU is its architecture. Unlike a CPU that has to be a jack of all trades, the NPU is built with a singular purpose. It's designed to handle massive parallel calculations, specifically the matrix multiplication and vector operations that are the bread and butter of AI models. Imagine you're sorting a massive pile of photos. A CPU would look at them one by one, which is slow. An NPU is like having thousands of little helpers who can all look at different photos at the same time and sort them instantly. This efficiency is key for running complex AI directly on your device, a concept we call on-device AI or edge computing. What does this actually mean for you, the user? It means your phone can do some incredible things without ever sending your data to a server. When you use your phone's camera to take a portrait mode photo, the NPU is what intelligently separates you from the background and applies that cool blur effect in real time. When you use live translation apps, the NPU is processing the language. It's also behind features like scene detection in your camera, voice to text on your keyboard, and even optimizing your battery life by learning your usage patterns. All of this happens instantly and privately on your device. The main takeaway for the NPU is that it's all about efficiency and locality. It's designed to be small, power efficient, and integrated directly into the system on a chip, or SoC, that powers your phone or laptop. This focus on low power consumption is critical for battery-powered devices. By handling AI tasks on its own, the NPU allows the much more power-hungry CPU and GPU to rest, saving precious battery life while still delivering a super snappy and intelligent user experience. It's the silent workhorse making your smart devices feel, well, smart. Now let's switch gears and talk about the other heavyweight in the ring, the TPU or Tensor Processing Unit. If the NPU is the nimble specialist in your pocket, the TPU is the industrial-strength supercomputer in a massive data center. TPUs are custom-designed hardware developed by Google, and their primary mission is to power Google's own massive AI and machine learning workloads. The Tensor in its name comes from TensorFlow, Google's popular open-source software library for machine learning. These chips are built to crunch the numbers for TensorFlow models at a scale that is almost hard to comprehend. The architecture of a TPU is what sets it apart. It's a type of application-specific integrated circuit, or ASIC, which means it was built from the ground up for one very specific application. In this case, that application is running tensor operations at lightning speed. TPUs use a clever technique called systolic array processing. You can picture it as a highly organized and efficient assembly line for data. Numbers flow through a grid of simple processors, each one performing a calculation and passing the result to its neighbor. This design allows TPUs to perform a staggering number of calculations simultaneously, with incredible energy efficiency for their performance class. So, where do you encounter the power of a TPU? Pretty much every time you use a Google service. When you search for something on Google, TPUs help rank the results. When you use Google Translate to understand a foreign menu, TPUs are doing the heavy lifting in the cloud. They power the image recognition in Google Photos, allowing you to search for dogs or beaches and get instant results. They're also the brains behind Google's conversational AI, like the Google Assistant and their advanced language models. These are tasks that require an immense amount of computational power, far more than any single device could handle. The key thing to remember about TPUs is that they are built for the cloud and for training AI models. Training a large AI model, like the ones that power chatbots or generate images from text, involves feeding it a colossal amount of data. This process can take weeks or even months on traditional hardware. TPUs slash that time down to days or even hours. They are available to developers and businesses through the Google Cloud Platform, allowing anyone to rent this supercomputing power to build and train their own sophisticated AI applications. They are all about maximum performance for the biggest AI jobs on the planet. So now that we know what NPUs and TPUs are, let's put them side by side for a proper tech showdown. The first major difference is in their core design philosophy and target environment. NPUs are all about edge computing. They are designed to be small, integrated into a larger chip system, and incredibly power efficient. Their main goal is to run pre-trained AI models, a process called inference, on a user's device. This means low latency, since there's no round trip to the cloud, and enhanced privacy because your personal data never has to leave your phone or laptop. TPUs, on the other hand, are designed for the data center. They are built for raw, unadulterated performance at a massive scale. While they can also be used for inference, their real strength lies in training gigantic AI models. Think about performance in terms of TOPS, or trillions of operations per second. A modern smartphone NPU might offer anywhere from 10 to 50 TOPS. A single Google TPU version 4 pod, which is a collection of thousands of TPU chips working together, can deliver over an exaflop of performance. That's a quintillion operations per second. It's a completely different league of power. This difference in scale naturally leads to a difference in flexibility and cost. NPUs are part of a broader category of hardware, and different manufacturers like Apple, Qualcomm, and MediaTek have their own unique designs. This leads to a diverse ecosystem but also some fragmentation. They are relatively inexpensive to include in a consumer device's main chip. TPUs are a proprietary Google technology. You can't go out and buy a TPU to put in your PC. You access their power by renting time on Google's cloud servers, which can be a significant operational cost for businesses. But it gives them access to state-of-the-art hardware without the massive upfront investment. Finally, let's talk about energy efficiency, but in their own contexts. An NPU is a champion of performance per watt on a mobile device. It sips power compared to a CPU or GPU doing the same AI task, which is crucial for preserving battery life. A TPU is also incredibly energy efficient, but for the data center, it delivers more computational power for every watt of electricity consumed, compared to using a vast array of GPUs for the same large-scale training task. So, while both are efficient, they are optimized for completely different power envelopes and thermal constraints, one for your pocket, the other for a climate-controlled server farm. Alright, so it's one thing to talk about the tech specs, But it's another to see where these chips actually live and what they do. Let's start with NPUs. They are honestly everywhere in the consumer tech space, even if they aren't always called NPU. Apple has its neural engine, which is a core part of their A-series chips in iPhones and M-series chips in Macs. This is what powers Face ID, live text in photos, and Siri's on-device processing. It's a prime example of an NPU that's deeply integrated into an ecosystem to provide a seamless and private user experience. Then you have the big players in the Android world. Qualcomm's Snapdragon chips, which power a huge number of flagship Android phones from companies like Samsung and OnePlus, feature their own Hexagon processor. This is their version of an NPU, and it handles a similar range of on-device AI tasks, from camera enhancements to real-time translation and voice assistance. Similarly, Samsung has its own line of Exynos chips with a built-in NPU, and MediaTek's Dimensity chips also feature what they call an APU, or AI Processing Unit. The name might change, but the function is the same: smart, efficient, on-device AI. On the TPU side of the fence, the examples are less about individual devices and more about the services they enable. The most prominent user of TPUs is, of course, Google. Every time you use Google Search, Google Photos, or Google Translate, you are tapping into the power of TPUs working tirelessly in Google's data centers. They are the invisible infrastructure behind the magic. For example, the technology that powers Google's real-time conversational mode in the Translate app relies heavily on TPU processing in the cloud to handle the complex language models required for fluid, two-way conversation. But it's not just Google's own products. Through Google Cloud, other companies can leverage TPU power for their own ambitious projects. For instance, a medical research company might use cloud TPUs to train an AI model that can detect diseases from medical scans far faster than humanly possible. A ride-sharing company might use them to optimize its logistics and predict demand in real time. Any business that needs to train a massive, complex machine learning model without building its own supercomputer is a potential customer for Google's TPU infrastructure. It's a B2B powerhouse. So why would a company choose to develop or use an NPU over a TPU, or vice versa? The decision almost always comes down to the specific problem they are trying to solve. It's a classic case of using the right tool for the right job. Companies that make consumer electronics, like Apple or Samsung, are obsessed with the user experience on their devices. For them, investing in a powerful NPU is a no-brainer. It allows them to introduce compelling AI features that are fast, responsive, and, crucially, private. The privacy angle is a huge selling point for NPUs. By processing data directly on the device, companies can tell their customers that their personal information, like their photos or voice recordings, isn't being sent to a remote server. This builds trust and sidesteps a lot of potential privacy concerns. Furthermore, on-device processing means features work even when you have a poor internet connection or are in airplane mode. For a smartphone maker, that reliability is paramount. The NPU is the key to unlocking this on-device intelligence without destroying battery life, making it the default choice for the mobile world. The choice to use a TPU is driven by a completely different set of needs. A company would turn to TPUs when their ambition is to build and train a foundational AI model from scratch. This is the domain of large-scale AI research and development. Imagine you are a startup trying to build the next great AI image generator. You need to process a dataset of billions of images. This is a task that would be impossible for an NPU and would be incredibly slow and expensive using traditional GPU clusters. The TPU offers a specialized, cost-effective path to training that model at speed. Ultimately, the choice isn't always either-or. In fact, NPUs and TPUs often work together in a complementary system. A company like Google uses its massive TPU farms to train a new, more efficient language model. Once that model is trained, it can be optimized and shrunk down to a smaller size. This smaller distilled model can then be deployed to run on the NPU inside millions of pixel phones. The TPU does the heavy lifting of creation in the cloud, and the NPU handles the efficient execution of the final product on the edge. This cloud-to-edge pipeline is a powerful combination that leverages the strengths of both architectures. The rise of NPUs and TPUs isn't just a niche technical development. It's a fundamental part of the broader AI revolution we are all living through. These specialized chips are the engines making widespread AI adoption possible. Before their existence, most AI processing had to be done on powerful but inefficient CPUs or expensive power-hungry GPUs. This created a bottleneck. AI was either too slow, too expensive, or too draining on the battery to be practical for many everyday applications. These new processors shattered that bottleneck. NPUs are democratizing AI by bringing it to the edge. By placing a capable AI processor in every new smartphone, laptop, and even car, they are making advanced intelligence a baseline feature, not a premium luxury. This is leading to a Cambrian explosion of new applications and capabilities. We're seeing smarter digital assistants, more helpful accessibility features for users with disabilities, and cameras that can practically think for themselves. The NPU makes AI personal, immediate, and context-aware, weaving it into the fabric of our daily interactions with technology in a way that feels natural and seamless. Meanwhile, TPUs are pushing the boundaries of what AI can achieve at the highest level. They are the supercomputers powering the development of large language models and generative AI that have captured the world's imagination. Without the massive computational power provided by TPU farms, training models like Google's Gemini would be practically impossible. TPUs enable researchers and developers to iterate faster, experiment with more complex architectures, and tackle problems that were once the stuff of science fiction, from breakthroughs in drug discovery to creating more accurate climate change models. Together, they create a virtuous cycle of AI development. The massive models trained on TPUs in the cloud set new benchmarks for what is possible. Then the race is on to distill and optimize these capabilities so they can run efficiently on the NPUs in our pockets. This constant push and pull between the cloud and the edge accelerates the entire field. The cloud provides the raw power for innovation, while the edge provides the platform for mass deployment. It is this symbiotic relationship that is truly fueling the exponential growth and integration of AI into our world. Looking ahead, the trajectory for both NPUs and TPUs is all about more power, greater efficiency, and deeper integration. For NPUs, the next frontier is moving beyond simple task acceleration to enabling more complex always-on AI experiences. We're already seeing this with the push for on-device generative AI. Imagine your phone being able to summarize your emails, draft replies, or create images for you, all without needing an internet connection. To do this, next-generation NPUs will need to be significantly more powerful and have access to more memory, all while maintaining their strict power efficiency. The market trend for NPUs is clear. They are becoming a standard, non-negotiable component of any competitive computing chip. The performance of a device's NPU is becoming a key marketing point, just like the number of CPU cores or the amount of RAM used to be. We'll see them become more programmable and flexible, allowing developers to run a wider variety of AI models on them. We can also expect NPUs to pop up in more places, not just phones and laptops, but in smart glasses, home robots, and all sorts of IoT devices, making our entire environment more intelligent and responsive. For TPUs, the future is about scaling to even more astronomical heights. As AI models continue to grow in size and complexity, the demand for computational power will only increase. Google will undoubtedly continue to develop new generations of TPUs, each one more powerful and efficient than the last. The goal is to reduce the time and cost of training the next wave of foundational models, potentially enabling AI that can reason, plan, and understand the world in much more sophisticated ways. We might also see more specialization, with different types of TPUs designed for specific kinds of AI models. The convergence of these technologies is also a key part of the future. The line between training and inference, and between the cloud and the edge, will continue to blur. We will see more hybrid AI models that do some processing locally on an NPU, and offload more complex parts to the cloud, powered by TPUs. This flexible approach will allow for a best-of-both-worlds scenario, providing the responsiveness of on-device AI with the power of cloud-based supercomputing. The continued coevolution of NPUs and TPUs will be the bedrock upon which the next decade of technological progress is built. So, after all that, what's the final verdict in the NPU versus TPU showdown? The real answer is that it's not a competition. There is no single better chip. Instead, they are two sides of the same revolutionary coin, each perfectly designed for its role in the AI ecosystem. The NPU is the champion of personal, on-device intelligence. It's what makes your everyday devices faster, smarter, and more private. If you care about your phone's camera quality, battery life, and the snappiness of its smart features, you care about the NPU inside it. It's the hero in your pocket. The TPU, on the other hand, is the undisputed king of large-scale AI. It's the engine that powers the cloud services you use every day and enables the creation of the mind-bending generative AI that is reshaping industries. If you're excited about the future of AI, from scientific breakthroughs to the next generation of powerful digital assistants, then you should be interested in the power of TPUs. They are the giants working behind the curtain, doing the heavy lifting that pushes the entire field of artificial intelligence forward into new and uncharted territory. Understanding the difference between these processors is more than just tech trivia. It gives you a better grasp of the forces shaping our future. When a company announces a new device with a 50% faster NPU, you'll know that means more capable on-device features and better privacy. When you read about a breakthrough in AI research, you'll understand that the massive computational power of something like a TPU likely made it possible. This knowledge empowers you as a consumer and helps you see through the marketing hype to understand the real-world implications of these technologies. Ultimately, both NPUs and TPUs are crucial. They represent a fundamental shift in computing away from general-purpose processors towards specialized hardware designed to tackle specific, complex problems. This specialization is what's unlocking the full potential of artificial intelligence. It's making AI more accessible, more powerful, and more integrated into our lives than ever before. So while they may operate in different worlds, one in your hand, the other in a faraway data center, both are essential pieces of the puzzle, working together to build a smarter and more capable technological future for all.